Good morning children. Welcome back to your chemistry class. Today in this chapter of metallurgy, we shall be talking about refining of the crude metals, and we shall also discuss about two metallurgies. Okay, so let us begin with the refining of the crude metals. So you know that the removal of the impurities from the isolated metal, that is called as refining of the metal, right? In other words, we can also say what? Refining of the metal is your purification of the metal that is obtained after reduction, right? So there are different techniques of this metal refining. So what in your syllabus you have? They are like distillation, okay? Then you have liquation. Then the third one that you have is your by the process of electrolysis, or what we can say is electrolytic reduction. Then you have to study zone refining. Okay, and also the Mond process. So these are the different methods for refining different types of crude metals. So let us first discuss about distillation. This method, it is used to purify the volatile metals, which like that of zinc, whose boiling point is 907 degrees Celsius. It can be also used for mercury. They can be zinc and mercury, right? In this method, the impure metal, it is heated in a big container. Then more volatile components, they evaporate first and they leave the less volatile component behind. Is this point clear in distillation? Secondly, if any impurity is more volatile, it is always collected in a separate container, and the metal which is desired, it is left in the original container. Then in this desired metal, if it is more volatile, then it passes away as vapor and it can be further condensed separately as pure metal, whereas the impurity is left behind. I hope this method is clear to you. So distillation means what? It is completely based on the difference of the boiling point between the metal and its impurity. I hope this is clear. Now let's talk about liquation. This method, liquation, it is used preferably for crude, tin, lead, bismuth. They are all purified by the process termed as liquation. So let me write down over here. It could be lead, it could be your bismuth, and which one I told you? Tin, that is Sn. So these metals can be purified by this method. So in this technique, the ingots of the impure metals, they are always placed at the top of a sloping heat and they are maintained at a very high temperature. The metals, they melt and they flow down the inclined heat into a receiver, and what happens to the impurity, the solid impurity, it is left behind. So this method is applicable only in those cases where there is large difference in the melting point of the impurity as well as the metal. So this refining of the metal by liquation, I hope it is clear. So this is preferably for which metals? Like lead, bismuth and tin, which have low melting point as compared to their impurities. Next, let's talk about electrolytic reduction. This one you very well know. In this technique, we use to purify the metals. Like for example, we purify copper, then zinc, aluminium and so on. Silver even can be purified by this electrolytic reduction. So in this process of electrolysis, what do? We need an electrolytic cell. Then we have a the anode and the cathode. What should be your anode? The thick block of impure metal. It is always your anode and it is connected to the positive terminal of the battery. And what is your cathode? It is the thin strip of the pure metal which is connected to the negative end of the battery. And now both these electrodes, they are connected to a battery, right? Now talking about the electrolyte, the aqueous solution of the salt of that desired metal to be electroplated at cathode should be your electrolyte, which should be present in the container. Now I hope you all know very well the process. The negative ions, they are going to move towards the anode called as anions, and the positive ions are going to move towards cathode, get deposited there as cations. And this way, by this process, what happens? The cations, they continue to move towards cathode. How? From the electrolyte as well as from the anode, and they get reduced. At the same time, oxidation will take place at anode also, as long as the current is flowing. Thus, what happens at the end? What do we observe? That the cathode is becoming thicker and your anode becomes thinner. So the impurities of the anode, they are always collected at the bottom of the cell, and what is that called as? Anode mud. And when your complete process is over, you will find that both your cathode and your anode both are in their pure form, where the cathode becomes your thick rod and your anode has become your thin rod. So this was your electrolytic reduction. Now let's talk about zone refining. Now what do we mean by zone refining? The zone refining, it is a technique which is used to obtain ultra pure sample. To remember, what did I say? To obtain ultra pure sample. So in this process of refining, the impurity, it is reduced to 1 part per billion. Can you imagine that? That ultra pure sample is obtained by zone refining method. So how does this zone refining method takes place? So the working of the zone refining, it is completely based on the principle of fractional crystallization, right? So in this purification, more effective when the melting point of the impurity is lower than the melting point of your desired metal. That is why this impurity is more soluble in the molten metal. So over here in zone refining method, the impurities, they are more soluble than the solid state of the metal. Like for example, the metalloids of high purity, they can be purified by this zone refining process. Clear? So just to give you a short explanation as to how it takes place. So for this we take an impure metal rod. Suppose this is your impure metal rod. Okay, this is your impure. This is your metal rod to be purified. Okay. So over here, suppose this is your X end and this is your Y end, right? A movable heater is attached over here to one end of the metal rod. Suppose this is your movable heater. So I write over here, this is your movable heater, right? So this heater, it moves from one end X towards the end Y. The portion of the rod intact or in contact with this heater, it melts. So suppose it is intact over here. This movable heater has reached here. So what will happen to this rod? This rod is going to melt over here, right? So this will be termed as your molten zone. What is this going to be called as? Molten zone area. As the heater, it moves forward, as this is moving forward, the molten zone also moves forward, but now it will come over here. This zone is going to get melt. As it is going to reach here, this zone is going to melt. So as this heater is moving forward, the molten zone is also moving forward. But the portion that is left behind the heater, it gradually solidifies. As this heater is moving, the back part of it is gradually getting solidified. So the impurity which is being more soluble in the molten metal, it is also carried away along with this movable heater towards the end Y of this rod. So by repeating this method or the movement of this heater from end X to end Y, most of the impurity is transferred from this X to Y end, right? And thus the end of the metal rod where the impurity has to be accumulated, it is, suppose it has accumulated over here, this portion is cut off, removed, and we obtain the pure desired sample. Pure form of sample is obtained over here. And what example did I give you? Mostly the metalloids or the metals which are used as semiconductors, they are refined by this zone refining process. I hope this is very clear. Now next we come to the Mond process. This Mond process is used for purification of nickel, generally for the nickel, right? So in this process, the impure nickel, it is treated with carbon monoxide. This nickel, it is treated with carbon monoxide at a particular temperature. What is that temperature? The temperature could be like 333 Kelvin, right? And this nickel then reacts with this gas and the gaseous nickel carbonyl will be formed. What did I say? Nickel carbonyl, that is NiCO4. This is your nickel carbonyl is formed over here. So the solid impurity, including the cobalt which is present in the nickel, can be easily separated. Now this pure nickel is removed from this carbonyl compound from here by heating it to a higher temperature. So if we heat this to 453 Kelvin to say 473 Kelvin, then easily we will obtain nickel in the form of a solid and carbon monoxide in the form of a gas will be removed. So this carbon monoxide gas can be recycled over here again with the nickel to obtain the nickel carbonyl, and from there we can obtain the nickel at the particular temperatures. So this process is called as what? Mond process, and preferably this Mond process is for nickel, refining of the nickel. So these were certain methods for refining of your crude metals. I hope this much is very clear. Now we shall move to certain metallurgies. Let us talk about metallurgy of iron. Okay, today I am using a different pen whose nib is not so very good, so I hope you are able to understand what I am writing over here. Okay, so we are going to talk about the metallurgy of iron. So what is the ore required over here? The ore required is your hematite, that is Fe2O3, right, which is also called as hematite. Now for next method is your concentration method. Not much impurity is present in this ore, right? So what are the different methods that can be used? Because it is an iron ore, so one of the methods could be your magnetic separation. Do you remember your different methods of concentration? That is your magnetic separation can be one of the methods, right? And another method of concentration for hematite could be even your gravity separation. By gravity separation also we can do the dressing of this ore, right? Now next we talk about calcination. Calcination or roasting, because it is an oxide ore, so we need calcination. No excess of air is oxygen is required over here. So in limited supply of oxygen, we obtain an ore which is free from moisture, and all the impurities like your sulfur or phosphorus or arsenic, they all can be removed over here by this method, right? So once again, calcination is the process where ore is heated in the limited supply of oxygen. So when it is heated in the limited supply of oxygen, in limited supply of oxygen, firstly it becomes free from impurities, right? What are those impurities? All the impurities, like your sulfur is there, it will combine with oxygen, it will remove as sulfur dioxide. Phosphorus present there will be removed in the form of P2O5, or even if arsenic is present there, it will also be removed as arsenic oxide. Clear? Now this I am talking about hematite. Suppose if I take a hydrated iron oxide also as its ore, maybe like let me take Fe2O3.3H2O. Okay, so this also by the process of calcination can give us Fe2O3 plus 3H2O, right? So this hydrated iron oxide can also be calcinated to obtain this oxide further. This also becomes free from the impurities. All the impurities can be removed. Another ore like your siderite, FeCO3. What is this called as? Siderite. Now this is a carbonate ore, so this also needs calcination. So in general, what am I saying? All the ores of your iron, they are always calcinated. And so on calcination, what do we obtain? We obtain iron oxide plus carbon dioxide gas is given out. So after this, now since we have obtained the oxide ore which is free from the impurities, we next move to the step that is called as smelting. So what is smelting? When the metallic oxide, it is reduced in the blast furnace by melting that particular oxide at high temperature. Clear? And for this, what do we use? We use a reducing agent. So which reducing agent are we going to use over here? We can use carbular coke, right? So if you see the figure over there of the blast furnace, see it has a cup and a cone arrangement on the top. The top and the bottom part of the furnace, it is narrow, whereas in the middle, if you will see, it has a wider area. Then the steel furnace is always linked with the fire bricks from inside, right? Now what will we see from the cup and the cone arrangement? Here, from here we are going to add the charge. So what is the charge that we are going to add over here from the cup and cone arrangement? The charge that we are going to drop from the cup and cone arrangement, it contains the ore which is 8%, right? It also contains limestone which is 1%, right? And this it is used as flux. This limestone is used as flux over here, right? And we also add coke which is used as a reducing agent. Is this point clear? So what are we doing from the cup and the cone arrangement? We are adding the charge. Now what is the charge? What does the charge contain? It contains 8% ore. It contains flux which is 1% limestone, and it also contains a reducing agent, that is the coke. Now also this helps to prevent the heat loss during the process of the reaction of this charge. I hope till here everything is clear. Now look at the bottom. Bottom you will find the tiles through which the hot air is blown inside the furnace, and the tapping hole is there to collect the melted ore, and the slag hole, it is used to collect the slag separately. Now if you look at the figure, again there are 4 zones, okay, where the reduction takes place or the reaction to obtain the metal takes place. Now let us look at the 4 zones where the different reactions takes place. So the first one, if you check the figure over there, it is called as the combustion zone, right? This is the lowest zone where the temperature is maintained at around, it is the, let me write down, lowest zone where the temperature maintained, it is around 1775 to 2000 Kelvin. This is the temperature maintained over there. What happens over here in the lowest zone? Here the coke, that is the carbon, it combines with the oxygen which is being pushed into the blast furnace, and this gas, carbon dioxide, is formed which rises up. This gas rises up in the blast furnace, right? It moves to the second zone, which is called as the reduction zone. Over here, this is the uppermost zone, okay? This is the uppermost zone, right? Over here, the temperature maintained is around 520 to 1075 Kelvin. What will happen over here? The carbon dioxide that has come over here from the combustion zone, it combines with the coke lining, and what is it going to form? Carbon monoxide. Now this carbon monoxide, it now acts as a reducing agent. So what it is going to do? You had already dropped the charge from the cup and cone arrangement. So over here, it is going to react with your ore and help us to obtain the metal, right? The spongy iron that we are going to obtain over here. So when this Fe2O3 combines with your reducing agent carbon monoxide, it will form Fe3O4 plus CO2. Next, this Fe3O4 in continuous carbon monoxide, it is going to form FeO plus CO2. Next, this FeO further is getting reduced to give you the iron and carbon dioxide. So I was talking about this iron.